For the final lab, I decided to use the knowledge gained throughout the semester to analyze the complexity of a falling slinky. This lab measures the slinky's motion from being expanded and then dropped from rest. The observed motion of this object will be measured and compared to a computational model to see how different forces affect an object's position. The results show that with more forces taken into account, an accurate representation of a slinky falling can be obtained as the observed model ended with a position of negative 1.792 meters in the y component, and the predicted model ended with a position of negative 1.794 meters in the y component. In order to look at motion, Newton's second law is needed. This law states that a force is applied on a system when there are interactions between objects. All these interactions can be added up to equal one net force, which can be measured as a change in momentum over a change in time. In this lab, the slinky is being dropped from rest. Since the initial velocity of the object is zero and then speeds up, this indicates that there is acceleration and a non-zero net force due to the momentum principle. One of the forces that is well aware is gravity, or the force of the Earth on the object. The gravitational force is proportional to the object's mass and has a specific constant known as Earth's gravitational constant of 9.8 newtons per kilogram. This constant comes from the gravitational law. When multiplied by the opposite direction vector, the gravitational force on the object can be calculated. This number is negative in the y direction since the object is falling towards the Earth. The atmosphere is made up of many particles, and these particles will have interactions with falling objects. These interactions result in drag force. From a previous lab, the drag force was specified as being proportional to the square of the object's speed times some proportionality constant. The drag force will be pushing against the falling object, so the value needs to be in the opposite direction as the velocity vector. Since the slinky is being expanded, the last thing that needs to be considered is the force the slinky has on the bottom of the slinky. When the object is dropped, the tension is still the same in perspective from the bottom, so the slinky will not move until the top of the slinky has reached the bottom. With these three forces added together, the net force on the slinky can be calculated. Using Tracker, the motion from the video of the object falling from rest was able to be measured. The center of mass of the object is indicated by the red dot in each frame as it moves in the negative y direction. The corresponding table and graph show the relationship of position versus time. As shown from the slow motion video, the bottom of the slinky remains motionless as the tension force is equal and opposite to the gravitational force, just as it was at rest. So the bottom of the slinky was chosen to analyze this type of motion. The mass of the object was 0.25 kilograms, estimated by the average metal slinky, and the initial position of the object is located at 3.1 times 10 to the negative 2 meters in the x component and negative 1.286 meters in the y component. The amount of time it takes for the slinky to reach the ground is 1.714 seconds, and since the object is being dropped from rest, the initial velocity is 0 meters per second in all components. As the velocity of the object increases, it is proven that there are forces interacting on the object. In the glow script code used to predict the motion of the falling slinky, the initial values from the observations are put in place, such as mass, position, velocity, gravitational acceleration constant, and the direction of the forces. The B component for drag force was determined to be 2.6. In the first while loop, the time was indicated to represent when the bottom of the slinky was motionless. The forces interacting with the object during this time was just the gravitational and tension forces, which are equal but opposite to each other. The velocity was updated from Newton's second law, and the update position formula was written into the code. In the second while loop, the time was indicated to represent when the bottom of the slinky was in motion. The forces interacting with the object during this time was the gravitational and drag forces, as indicated during the fundamental principles. The velocity and position update formulas were coded as well. The results show that the predicted and the observed values are very similar, except for a few discrepancies once the object started falling. This could be due to the fact that the slinky may have continued forces acting upon itself. It was originally analyzed that as the top of the slinky came in contact with the bottom of the slinky, it continued to fall as one, but there could still be tension and other factors contributing to the fall of the slinky. In the future, I would try to analyze both the top and bottom parts of the slinky to see if velocity changes with contact or if additional forces need to be included. Overall, this lab indicated how multiple forces can impact the falling object even if one of those forces is coming from the object itself.